Okay. Thank you. All right, can you hear me? So I've been obliged to tell you that the talk will be recorded. So there you go. So it gives me great pleasure to actually be here. When I first started programming, I wrote a lot of Pascal and Modulo 2 code, so the ETH has a special place in my heart as the origin of those languages. And so what I'm going to talk to you today about is using deep learning to solve challenging problems. And I'm going to point out this is joint work with many, many people. I'm presenting the work of others in some cases. Sometimes it's myself with many, many collaborators. But first, let me tell you a little bit about how we organize our research activities at Google. So first, we have offices all around the world for research activities, many in Mountain View, in Zurich, in Paris, New York, and all the other places you see. We're excited to have recently opened our first research office in Africa and Ghana, and other places. So research is kind of nice because you can actually do it all over the world, and you need less tight coupling between sort of people doing things than more product engineering oriented things. So, but our basic approach in research is we kind of divide things we do into 4 rough buckets. So first, we conduct basic research. We try to tackle ambitious problems and have impact by working on them and making progress on them. We publish about 500 research papers a year in the last few years across nearly every area of computer science, beyond. We build infrastructure is the second sort of area to enable this research. So software infrastructure, in some cases we collaborate with people and help build hardware infrastructure, and then allow it to be widely utilized. So it's really good to take a research idea and then build infrastructure so 10 teams can use it rather than working one-on-one with an individual team to try to get something used. We also collaborate with Google product teams to help use the research that we've done in product contexts where it makes sense. So we've done a lot of collaboration in the past with the Google Translate team, Google Photos team, Search, Ads, Gmail, Waymo, many, many, many others. And then we conduct research that's applied to kind of new or emerging areas. And we have pretty big efforts that I'll talk a little bit about today in using machine learning for healthcare and also machine learning for robotic control. We have lots of ways that we interact with academic institutions. So for faculty in the audience, we have many different kinds of awards. We have visiting faculty. For students, we have various kinds of fellowships and internships and travel grants to different conferences. But let's set the context. So the field of machine learning is undergoing like an explosion of interest and new people entering the field, doing all kinds of interesting things. This is a graph of the number of machine learning archive papers posted per year in this sort of subfields of Arxiv that are related to machine learning. And the interesting thing is it's undergone tremendous growth in the last sort of 8 or 9 years. And in particular, it's actually growing faster than the Moore's Law exponential growth that we experienced in computing power for many years of 2x every 2 years. So that's that red line you see there. It's actually growing faster than that. Unfortunately, we're not getting the Moore's Law computational growth these days, but we've replaced it with generation of machine learning research ideas. And maybe that will help make up for that. So that's exciting. There's lots of new people entering the field and so on. And the particular subfield of machine learning that is getting a lot of attention is so-called deep learning, which is really a modern rebranding of artificial neural networks, which have been around for quite some time. And this has this nice property that it's a collection of these simple trainable mathematical units that work together and can solve pretty complicated tasks. There was a wave of excitement about neural nets in the 80s and 90s. As they sort of, the sort of algorithmic pieces sort of fell together. And ultimately, people were excited because they could show interesting results on kind of very small scale problems at that time. I actually did an undergraduate thesis on parallel training of neural nets because I felt like the abstraction was a good one. And we just needed more compute. So maybe we could get like 60x speedups by using a 64 processor machine, and it would all be good, and we could solve really big problems. Turns out we needed like 1 million times more compute, not 60. But we now have that, and that's why you're starting to see these really impressive sort of new results that are coming out of using artificial neural networks for tackling different kinds of tasks. So let's talk about a few things that neural nets can do. So obviously, computer vision
You've probably heard that it's now been taken over by artificial neural networks. You can feed in the raw pixels of an image and get out a categorization of that image simply by training a model on lots of examples of images and different classes of labels. And they can be pretty fine-grained labels, 1,000 different categories, 10,000, 50,000, that's fine. You can put in audio waveforms and get out a transcript of what was said in that audio waveform. You can put in language in one language, words in one language, hello, how are you, and get out bonjour, comment allez-vous in another language. You can put in the pixels of an image and get not just a classification, but a sort of a sentence, a simple structured sentence describing that scene, a blue and yellow train traveling down the tracks. So, these are, pretty interesting in that the same general techniques apply to all these different domains. And in computer vision, just to give you a sense of the progress in the last few years, in 2011, the ImageNet contest that Stanford administers every year did not use a neural net. So that was the year before people started using neural nets for this contest. This is basically take a color image and produce one of 1,000 different categories for this task. And the winner that year got 26% error. We know humans have about a 5% error on this task. It's actually pretty hard. There's lots of different sort of fairly precise categories of dogs and so on. So it's not sort of trivial for humans. And in 2016, we now have 3% error, right, for the winner. And that's really sort of transformational, right? If you think about that, computers basically didn't used to be able to see very well, as little as 6 or 7 years ago, and now they can actually see. Right? So if you think back to the time in evolution when animals evolved eyes, that's sort of where we are in computing, is we now have the ability for computers to perceive the world around them fairly well, and that has all kinds of implications. Okay, so the rest of the talk I'm going to frame as a discussion around the US National Academy of Engineering list of grand challenges for the 21st century. So in 2008, the US National Academy of Engineering convened people from a bunch of different scientific and engineering disciplines together and said, what should we really as a community be thinking about solving in the 21st century? And after much debate, they came up with this list of 14 different topics. And I think you can agree that if we were to make significant progress on some or all of these, the world would be a better place. We'd have healthier people, the world would not be getting so hot, and all these kinds of things. And I actually think machine learning is going to be a significant factor in helping us tackle all of these. But I'm going to talk today about the ones in red. Okay, so one of them was restore and improve urban infrastructure. And we're actually on the cusp of a pretty exciting change in how we transport people around the world, which is the deployment of self-driving cars. You've been hearing about these for quite some time, but a self-driving car fundamentally is trying to understand the world around it through fairly raw sensor data. It's taking in, images from a bunch of cameras and a radar and a LiDAR that gives you sort of 3D point cloud information. And then it needs to fuse all that information together into sort of an understanding of the objects in the world around it, how those objects might move. Is that a fixed object or is that a pedestrian that might dart in front of my car? And then make safe decisions to navigate the world, including understanding all the traffic laws and the signs around it. And to give you a sense of where we are in this, Waymo is Google's or Alphabet's self-driving car subsidiary. We collaborate closely with them. They've been running trials for many years, and they've actually started earlier this year in Phoenix, Arizona, doing trials of about 100 cars with passengers in the back seat and no safety driver in the front seat. So this is not some distant thing. This is actually, a pretty serious assessment that they feel pretty confident that these cars are ready. Now, Phoenix is an easier driving environment than many, but this is close. Obviously, vision is an important aspect of robotics as well. If you can see, it's much easier to build a robot that can do interesting things in a less controlled environment. So, one of the things we've been doing is building up a sort of parallel hardware lab of different robotic arms so that robots can experiment with different things or be told to experiment, and then can pool the experience that they gather in order to sort of improve their collective ability to do things. And in particular, one task we've been focusing on is grasping. It's a very primitive kind of thing. You have to essentially be able to grasp things if you want to do much else in the world. And so the first thing we did was explore supervised learning with this parallel set of about 10 robotic arms. And the nice thing about grasping is it's a completely self-supervised task. So if you try to grasp something and you fail, your gripper closes all the way, and you can tell that you failed. But if it succeeds, then you can tell that you've successfully picked it up. And so you can essentially buy a bunch of different kinds of varieties of objects, put them in a bin in front of it, and the robot can practice 24 hours a day, picking things up and pool that experience. And so with that, we were able to actually do about 800,000 grasp attempts in a few weeks and get to a 78% grasp success rate. Prior to that, it was just about the mid-60s. So that's still not fantastic. And so since then, in the last couple of years, our robotics research group has been working on using better algorithms for this and a few other kinds of things. And so these grasp success rates are grasp success rates for new unseen objects never seen during training. And so now we're at a 96% grasp success rate. And if your grasp success rate was mid-60s, it's very hard to sort of build any sort of reliable robotic system with that grasp success rate. But now we're getting to the point where you can actually sort of count on being able to reliably grasp something and do something with it. Another thing that we think is important is the ability to give robots new skills in a much easier way than we've traditionally done that. Traditionally, people have handwritten robotic control algorithms for very specific things, which is why most robotics work to date that's had significant widespread application is in very controlled environments where a hand-coded control algorithm can sort of very precisely decide what the robot should do. But in messy environments like this one, that's not really going to work very well because you have many variations that you need to deal with. And learning is really the approach that I think is going to get us there. And so we have a bit of work in this direction to try to get robots to emulate things that they observe in videos. So on the left, you see emulating kind of the behavior of the person. This is one of our AI residents. It is Switzerland, I guess. And on the right, what you see is a few different example videos of people pouring things, and then a robot that is a learned policy from observing that. So they observe about, I think it was 10 videos of this pouring into different shapes vessels, and then about 15 trials that took about 15 minutes, and the robot has learned a policy that is admittedly not perfect, maybe 4-year-old human, not 8-year-old, but actually being able to give the robot the ability to pour in that level of time is a pretty significant advance. Okay, another one of the grand challenges was advanced health informatics. And I think there's tremendous potential for machine learning to really be used in the field of healthcare to make better healthcare decisions for all of us. And I will touch on a couple of them. First, in the domain of medical imaging. It's very clear now that general computer vision has improved so much that we can actually use computer vision techniques to help with medical imaging diagnostic tasks. And so diabetic retinopathy is the one that we've decided to focus on initially. We've now branched out and we're looking at about 6 or 7 other modalities of pathology and radiology and so on. But I'll take you through the work we've done in diabetic retinopathy and ophthalmology-related problems. So diabetic retinopathy is the fastest growing cause of blindness in the world. There's about 400 million people at risk for this disease because it's a complication to diabetes. And really, if you're at risk because you have diabetes, you should get screened every year by an ophthalmologist to see if you have this degenerative eye disease. And really, that involves taking a picture of the back of your retina, and then an ophthalmologist looks at that image to interpret it. And in India, for example, there's a shortage of more than 100,000 eye doctors to do this screening. So not everyone can get screened as regularly as they should. And as a consequence, 45% of the patients suffer vision loss before they're actually diagnosed. And the way an ophthalmologist goes about this is they sort of look at these images and then they grade the image 1, 2, 3, 4, or 5, depending on whether they see particular kinds of hemorrhages, like I've highlighted here on the right, or other kinds of things, or if it looks reasonably healthy. And so if you want to have a computer system that does this, you can collect a fair amount of training data together and have ophthalmologists label these images, 1, 2, 3, 4, 5, and then you try to train an algorithm that can approximate that using a sort of an off-the-shelf general purpose computer vision neural network architecture that was developed for, say, ImageNet. Instead, you now have it predict one of these 5 categories on the retinal image. And if you do that, you now have a model, this was published at the end of 2016 in JAMA, that is basically on par or slightly better than the average US board-certified ophthalmologist at doing this task. And that's pretty good. We'd actually like to do better. Really, there are retinal specialists in the world, very few of them, who would actually be able to do this better than board-certified ophthalmologists. And so if you change the way you label your training images, so instead of board-certified ophthalmologists, you use people with extra training in these retinal diseases to label the images. And we actually also changed the protocol by which they label them. Instead of making independent assessments, we actually got 3 retinal specialists in a room to argue about each image and to decide, that one's a 2, this one's a 3, and so on. And now we have a model that is sort of on par with the average, the median retinal specialist. And that's kind of a higher standard of care that you would want everyone to receive throughout the world. And so that's what the beauty of ML applied to healthcare problems will allow to happen. The other interesting thing in ophthalmology problems is, so far, what I've told you is essentially replicating what human experts can do by training models based on their opinions. But we can actually make completely new kinds of systems that can see patterns in retinal images that ophthalmologists weren't even aware existed. And so, for example, if you try to predict a bunch of factors that are symptomatic of your cardiovascular risk from retinal images, we actually had some data where we actually knew, for example, the age and the gender of the owner of the eye. You can actually predict these things and then combine those predictions together to get a assessment of cardiovascular risk called a 5-year MACE. And the accuracy of that assessment is essentially equivalent to what you would get from a normally much more invasive blood draw. You would draw blood, send it off to the lab, wait 24 hours or whatever, get the results back. Now you can actually get that information immediately from a retinal image. So we think that's pretty interesting because that's information even ophthalmologists did not know you could tell gender from staring at a retinal image. The other kind of area in healthcare that we're looking at, one of the other ones, is given a patient's electronic medical record data in de-identified form, can we build models that can predict the future for a patient? So if you have a patient sitting in front of you with some previous medical records, maybe they're reporting some sort of symptoms, what can we do for that patient? And this is essentially a sequential prediction task. And lots of the progress in deep learning has been about how can we make sequential prediction models that are actually quite effective. And so in our research group in 2014, there was a paper published called Sequence-to-Sequence Learning with Neural Networks, which was sort of a fairly basic research kind of problem of how can you, conditioned on an input sequence, predict an associated output sequence. This sounds kind of abstract, but the translation example I gave you earlier is actually an example of using that sort of model. You have an input sequence in English, an English sentence, and conditioned on that English sentence, you now want to predict, what is the corresponding French sentence. So this was an interesting paper published without any particular product application, and as an example of how work kind of flows from this basic research throughout many different ways it could be applied. The Gmail product team, in collaboration with our researchers, built a system called Smart Reply, where now, based on an incoming email message, we can try to predict short responses that might make sense for that incoming message you've received. Hey, would you like to come to dinner on Thursday? Sure, I'd love to. No, I can't make it. Or, yeah, what can I bring? And now 12% of all mobile responses are sent using those automatically generated responses. The second system is the machine translation system that we worked with the machine translation team to use this explicitly for machine translation in the Google production scale. And then the third area, one of the other areas, is in medical records prediction tests. So given a big corpus of de-identified medical records, can we predict things that doctors might want to know? Will this patient be readmitted to the hospital if I allow them to go home right now? What are the lengths of hospital stay for a patient that's coming now? What medication should I think about prescribing? And we've been collaborating with several different healthcare organizations, including UCSF, Stanford, University of Chicago, on de-identified medical records to see how well this works. And we published a paper earlier this year in Nature Digital Medicine that assessed how well you could do by essentially using every piece of information in the patient's medical record to make these kinds of predictions. And so one of the things that clinicians and healthcare systems want to predict is mortality risk for a patient. Really, how likely is this, how much risk is this patient in? So that you can focus your medical attention on the patients that are really at high risk. And they currently actually use various kinds of fairly simple models for this. So they take about 20 extracted kind of hand-designed features, feed them into a model, and get a prediction for this mortality risk. And that's what you see on the dotted line here at different times relative to their admission. So in the middle is admission, 24 hours before and 24 hours after. And what you see is that if you use all the data in the medical record to make these kinds of assessments, you actually get up to the solid line for prediction accuracy. And that allows you essentially to get 24 hours earlier assessment at the same accuracy level for the patient's medical risk, for their risk of mortality. And that really means you can really pay attention to a patient a day earlier when they are, before they deteriorate too much, you hope. Okay, so many of the grand challenges were around this notion of basically understanding chemical properties or material properties. So I'm going to lump a bunch of these together and just give you an example of the kind of work that I think is going to be useful for all of these different areas. This is a problem in quantum chemistry where we've been collaborating with quantum chemists at the University of Basel, actually. Essentially, quantum chemists want to be able to take a molecule configuration and then predict various properties of that molecule configuration. Will it bind to this or that? Is it toxic? What are its quantum properties, and so on. And the way they typically do this is that they have a very computationally intensive HPC-style simulator called the Density Functional Theory Simulator, which sort of simulates things at a very fine-grained time-step scale. And in about an hour, given a molecule configuration, you get the data that you want. Now, it turns out you can actually use this simulator as a teacher for a neural network. So if you do this and you gather a bunch of training data of input and outputs from the actual simulator, you can then train a neural network to do this. And the actual outputs of the neural net are indistinguishable in accuracy from the original simulator, except that it's 300,000 times faster, right? And we've seen this actually in many different subfields of science. We had a visiting faculty member from Harvard who replaced the inner loop of an earthquake fault simulator with kind of a really, the world's lamest neural network. It was 4 layers and 10 neurons per layer and got like a 10,000 times speed up in the fault simulations. So if you're in the field of sciences and you have some simulator, think about this as a general pattern that you might recognize and it might be applicable. But anytime your tools sort of improve in time by 300,000 fold, then that really means you do a different kind of work, right? It's entirely feasible now to screen 100 million molecules while you go get coffee and come back and, you know, examine the 1,000 most interesting ones in some way. Okay, one of the vaguest of the grand challenges was engineer the tools of scientific discovery. I think they might have thrown this in as kind of a grab bag. Really, if machine learning is going to be at the heart of solving many of the other grand challenges, we should engineer tools for machine learning that allow us to express machine learning ideas easily and efficiently. And so TensorFlow is a system that our group has been working on for expressing machine learning research ideas, getting them into real production environments in wherever machine learning wants to run. You know, machine learning as it's spreading throughout our computational environments wants to run in many places. It wants to run on your mobile phone, it wants to run on your desktop machine, it wants to run in large data centers, many other places. And this is really an open standard for machine learning. We released it at the end of 2015 with a very flexible Apache 2.0 license, which sort of means take it and do whatever you want with it. We don't care. I'm not a lawyer, but that's roughly what it says. And it's actually had a pretty good uptake in terms of interest. So this is one sort of weak metric of interest, which is GitHub stars, people who star repositories so that they can follow updates and what's going on with them. That's TensorFlow in the purple there, and a bunch of other open source machine learning packages on the other lines there. And it's had a really nice development of a community around this. So both lots of people are using it for all kinds of things, but also people are coming together to help improve the underlying system, to make it run on Windows, to make it have better GPU support, to do this and that. So we now actually have 2 times as many contributors outside of Google as we have inside Google for, have actually checked in code contributions. And it's been downloaded, 16 million times, which is quite a lot for a sort of fairly obscure programming tool. And so, I hear stories of what people are doing with it, and these are just a couple that I've heard. There's a company in the Netherlands who builds fitness sensors for cows, right? This is like a healthcare for everyone, but for bovines. And they actually use TensorFlow to analyze the sensor data so that they can actually detect which of your 100 cows in your herd is behaving a little oddly and maybe limping or doing something differently. A group at Penn State University in the US and the International Institute of Tropical Agriculture in Tanzania collaborated to build a on-device machine learning model to detect cassava disease. So this is a cassava plant. It's actually the 3rd largest source of carbohydrates for people in the tropics. So it's a pretty important crop around the world. And it needs to run on device because you're out in the middle of a cassava field and you want to know what disease does my cassava plant have and how to treat it. And so that's what this application does. Another example of where you want ML compute to run where it wants to run. Okay, so another area that we've been focused on in our group is how can we make machine learning easier for people who don't have as much machine learning expertise. There's so many problems that machine learning should be applied to in the world, and very limited numbers of people who actually have significant training in how to apply machine learning. I would say there's probably 10,000, maybe 20,000 organizations in the world that have hired machine learning people who are actually deploying machine learning systems, but there's probably millions of organizations in the world that should be using machine learning in some way, but just have not hired such people, aren't even really thinking about it. So currently the way you solve machine learning problems is you have data and you have computation devices of some sort, and you have a human machine learning expert sit down and make a bunch of decisions about how they're going to approach modeling the problem, what kind of structures, models make sense, how should they prepare the data, and so on, and they kind of run a bunch of experiments and they throw it all together, and at the end of that you hopefully get a solution to your problem. But maybe we could automate some of what a human machine learning expert would do and turn this into data plus computation, giving you a solution for some kinds of problems. And that would be pretty cool. So one of the first directions that we explored in this space is something called neural architecture search. And the idea here is a human machine learning expert using neural nets sits down and makes a bunch of decisions. Should I use a 17-layer network or a 15-layer network? Should my filter sizes be 3 by 3 or 5 by 5? Should I use dropout or not? All these kinds of decisions require domain expertise and careful experimentation, and previous experience often helps you get into a good state. So here, what we're going to do is have a model generating model. So it's going to generate a description of a model, all those sorts of decisions that a human machine learning expert would make. And then we can train those models on the problem we actually care about. And then we can use the accuracy of those models as an indication of how well they worked, and then use that as a reinforcement learning signal to train the model generating model, essentially steering it towards models that seem to work pretty well and away from models that didn't work as well. And so that's the general idea, and then you repeat. So you repeat a lot, and eventually you come up with models that are generally more and more accurate over time as you sort of run these computations. Eventually, it kind of plateaus in accuracy, but you have models that are pretty accurate. So let's see, and they look kind of weird, right? Like human machine learning experts would not sit down and design that connectivity structure. But this is these kind of high, connections that jump many levels and allow you to skip many levels are actually reminiscent of ideas that human machine learning experts have come up with in some of their own research of skip connections. So for example, in the ResNet work out of Microsoft Research, every 2 layers has a connection that allows one layer to skip the one above it. And that the essential idea is you want information to flow more directly from the input to the output. And so these sort of organic style skip connections actually achieve a similar effect. Okay, so on this graph, I'm showing you accuracy of various kinds of ImageNet models on the y-axis and the amount of compute that those models require for an individual image to make one of these predictions. And every black dot here is sort of an important paper of the last 5 or 6 years that has advanced the state of the art in ImageNet in some way. And each one of them is sort of the result of years of effort by sort of the top machine learning researchers and computer vision researchers in the world, 5-author paper working together for 6 months or something. And if you apply AutoML to this problem, you end up there. And that's true both at the high end, where you care about the most accurate thing possible, and you're willing to pay pretty high computational cost. But it's also true where you might want a really cheap model that can run on your phone in the middle of a cassava field. And so that's pretty encouraging, right? That essentially by automating the experimentation process, the system is actually able to come up with models that are better than the black dots. And this has actually been released through Google's cloud products so that people in industries where they don't necessarily have machine learning expertise can upload labeled data sets of image problems they'd like to solve. Maybe they have 100 different kinds of parts in a factory they're trying to recognize, and they want to upload that and then get a trained, highly accurate model. This allows them to do that. And we've been following this thread and doing a bunch of additional work. So we've been exploring the use of evolutionary algorithms rather than reinforcement learning to see how well that works in comparison to RL. We've had a system that can learn new symbolic optimization rules. So if you're optimizing one of these neural nets, you usually use stochastic gradient descent, or maybe stochastic gradient descent with momentum, or maybe ADAGRAD or ADAM. There's a handful of these things that have been published in the past, and people generally use one of 4 or 5. We can actually learn how to combine symbolically different optimization update rules and get new and interesting functions, learn the nonlinearity to use instead of some of the ones that people have been exploring. As follow-on work to the AutoML, sort of the neural architecture search, you can actually modify the reward slightly so it takes into account both the latency of the model that it's exploring and the accuracy. And that enables you to say, I really want a model that runs in 80 milliseconds. And you can also even specify it needs to run in 80 milliseconds, and that's really my deadline. Or you can say about 80 milliseconds, but a little bit more would be fine. Data augmentation policies. So most of these vision models have a variety of pipelines that do things like resize the images to a particular size, maybe flip them horizontally sometimes, and then pick a random crop to use as a training example every time they go through the data set, so that you kind of extend the amount of uses you get from every individual image by making them all slightly different, but you know that the label still applies. It's still a horse, even though you've picked a random crop that has 80% of the horse in it or something. And then some work on exploring many architectures simultaneously with parameter sharding to make the cost of computation lower for this approach. Okay, but more computational power never hurts. And really, if you look at these algorithms that I've been discussing, deep learning is really transforming how we think about computation, right? It's not a matter of taking a bunch of random C++ code with ifs and thens and switch statements. It's really about 2 kinds of operations. The first properties that are nice are that all these neural net algorithms seem to be very tolerant of reduced precision. You can essentially use 1 decimal digit of precision And that's perfectly fine for these algorithms. Unlike traditional HPC style codes that are, you want 32-bit floating point or 64-bit even. And the other property they have is all the computations are essentially stitching together a handful of specific kinds of matrix operations or linear algebra operations in different ways. Matrix multiplies, vector dot products, things like that. So if you can essentially build computers that are really, really good at low precision linear algebra, that is a pretty flexible substrate on which you can actually express all these different kinds of machine learning algorithms I've been describing, but get great acceleration because your hardware only has to do this and nothing else. So part of the motivation for this was in 2012, we were starting to collaborate with our speech recognition team and image recognition teams, and we're getting like really good looking results. The speech recognition word error rate was dropping tremendously so that you could actually sort of start to really rely on it. And so I did this thought exercise. If our speech recognition is getting significantly better, what if 100 million of our users start talking to their phones for 3 minutes a day? Maybe they start dictating emails and who knows what. And the scary answer from some simple calculations was we'd need to double the number of computers that Google operated in our data center fleet for that particular feature. No, entirely just for that feature. And so that was pretty scary, and we realized that we really needed something that could accelerate the kind of inference needs we had for taking a trained model and then serving it with low latency for production uses. And so that's where we started in the hardware space, hardware accelerator space for neural nets. TPU v1, Tensor Processing Unit. The first one was for inference only, so it's not trying to target training. It's just saying you have a trained model, it's going to fit in the memory on this chip, and then this chip is going to have essentially just a lot of multipliers of low precision numbers, and that's pretty much all it's going to have. And that's been in production use now for about 4 years. It's used in every search query you do. It's used for all the translations you do, for speech, for image recognition. It was actually used, this 2-rack system here was used during the AlphaGo match that our DeepMind affiliates played against Lee Sedol in Korea. There you see the little Go board on the side in the data center. He was competing against Custom ASICs, I guess. And we published a paper in ISCA 2017 about that first chip. Then we decided we wanted to bite off the harder task of how do you design systems for both training and inference. Now that's harder because for training for large problems, it's very unlikely you'll ever get enough compute on a single chip for large problems. And so you really then have to start thinking holistically about an entire computer system rather than just a chip. How do the chips communicate at high speed and so on. So this is the device we came up with. It's called TPU v2, and it has 4 chips with about 180 teraflops of compute, and they're designed to be connected together. So if we zoom into one of the chips, it's actually a pretty simple design. That's part of the attraction of building these accelerators, is you essentially have a very large matrix multiply unit. So every cycle you get 65,000 results, scalar results in a 128 by 128 matrix. And you have scalar and vector units for the things that don't map naturally onto the matrix multiply unit. And that's pretty much it. And it's designed to be connected together into these larger configurations we call pods. So this is 64 of those, 256 chips arranged in a 16 by 16 mesh with wraparound links. So it's a 2D torus. And then a year later, in May, we announced the TPU v3, which is essentially a pretty similar design with some improvements to the core chip, plus water cooling, which actually allows us to run it at a higher power. And those are designed also to be connected together into a slightly different pod configuration that is, about 4 times bigger. And the overall system gives about 8 times the performance of the earlier pod. So there's 100 petaflops of compute, and that allows you to really tackle large-scale machine learning problems. And the important thing from that is both you can train large problems, but also you can use these to very quickly get results for a machine learning experiment you're trying. So in the same way that speeding up the quantum chemist tool by a lot, speeding up machine learning researchers' tools tremendously actually means that you do very different kinds of work if your results are going to run in 20 minutes than if they're going to run in 2 days. And these are all designed to be programmed via TensorFlow, so the same program runs minor modifications on these different platforms, and the same program scales via synchronous data parallelism, which is actually quite easy to reason about from a machine learning researcher perspective without modification on pods. And the Dawn Bench is a Stanford-operated, Stanford-run benchmark for machine learning tasks, both on sort of absolute training time on the left for one, this is one of the Dawn Bench tasks, image classification on ImageNet, so you have to get to 76% accuracy in a certain amount of time, well, as fast as you can. And TPUs hold the top 3 spots there, and training cost, if you measure the cost for things that have public cloud-based pricing, it actually takes the top two spots there. Oh yeah, I should mention, as part of that, we've been making these systems available to cloud customers who want basically a virtual machine with one of these devices attached, and then they can run, you know, arbitrary machine learning computations that they want on there. Okay, and we're also making 1,000 of those devices available for free to top researchers who really are committed to doing open machine learning research. So this could be machine learning researchers, could be scientists who have interesting problems they want to apply machine learning to, as long as they're committed to openly publishing the work that they're doing. And we're really excited to see what, you know, researchers are doing with this computation. Okay, another area I'll touch on is machine learning for systems. You know, if you think about computer systems, very few of the core things in computer systems are learned. So let's touch on one piece, which is index data structures for things like databases or key value stores. So if you think about what a B tree in a traditional traditional, say, sorted data structure for a database or a key value store does, is it takes in a key, and it's meant to then tell you, say, which disk page this key must exist in, if it exists at all, right? And the keys are sorted. So you're essentially taking this name or this address or part number and trying to say, where in my sorted list of part numbers must that part occur, if it occurs at all? So if you squint at that just right, that B tree looks a bit like a predictive model. It happens to work not with a machine learning method. It has like a multi-way branching tree. But if you squint at that sort of high-level specification, that sounds like something you could put a key in and produce a prediction. And that's essentially what this work does, is we replace the B tree with a small neural net that takes in keys and makes predictions of where that key is likely to fall in the sorted list of keys. So it's essentially trying to predict the position in the cumulative distribution function of that sorted list of keys, of where that key must go. And from that allows you to perform the same function a B tree does. And this actually works, which is nice. It's always good when that happens. So if you look at, this is an index of 200 million web service log records. The B tree performance of various metrics is on the top. And the learned index has the ability to be, you know, trade off accuracy and size of the learned index. So let's just pick one of the ones, the one that's in red. That system is 60% faster than the B tree, and it's 1/20th the space. And if you prefer, you could take the row above it and be 17% faster and 1% of the space. So this is like, again, a fundamentally different kind of thing. If your indices get 100 times smaller, that means you might think about what you index and how you index it differently. So where else could we use learning in computer systems? You know, I think computer systems in general are filled with heuristics, and those heuristics have to be written in such a way that they work well in the general case. Right? They don't adapt to how the system is actually being used generally. They don't take into account available context that might be available. To look at all these different places, you could imagine squinting at them just right and saying we should use learning here rather than heuristics. You know, instruction scheduling is littered with heuristics. Register allocation, which things should I spill? Loop parallelization strategies. Networking, should I make my TCP window bigger or smaller? Operating systems, which process should I schedule? which tasks should I co-locate on different machines in a large data center scheduling system, ASIC design, how should I lay out physical circuits. I think there's lots and lots of opportunities here. Within Google, we generally punt and say, well, I have something I could decide, or I could just make it a configurable option. And we have literally hundreds of thousands of command line flags scattered across our code base, many of them related to performance tuning kinds of things. And so you can imagine making all of those be a learned thing. How many event manager threads should my program use? I don't know. I'd have to run a bunch of experiments, but if the system could automatically figure that out, that would be much better for me. Okay, so I think there's a big opportunity here to make these systems much higher performance and more adaptive than they are today with the current handwritten heuristics. Okay, let me finally touch on thoughtful use of AI in society, right? It's pretty clear that these systems are now going to be sort of filtering out and being used in more and interesting ways throughout lots of different things that we see in society. Things like self-driving cars or medical diagnostic systems and so on. And it's really important to be thinking carefully about how we actually want to be deciding what uses of AI make sense. When we do use it, how can we make sure that it's safe, that it's unbiased? How can we make sure that it's understandable to people? What part of our medical records work that I didn't touch on is we've spent some amount of effort trying to make the predictions that it makes interpretable by clinicians, right? It's much better to say, patient needs heart valve replacement because of, this obscure phrase in a medical note a few years ago, this elevated test result in this. If you just say patient needs heart valve replacement, that's not a very actionable thing for a clinician. They really are sort of less likely to trust the decision if they can't understand why it's made. Privacy is a very sensitive thing for machine learning systems for certain kinds of data. So we've been thinking about these sorts of issues within Google for quite some time. We actually codified them in the set of principles that we published earlier this year. And I think these are good general principles. The important thing is we actually also are doing research, because some of these are not black and white things. They're gray areas, and we actually don't know necessarily how to make systems that are learned safe in the same way we have years of experience in building safe kind of hand-coded safety-critical things like avionics systems, right? We need that same engineering methodology for learned systems, and we're starting to get a handle on how to do that, but we definitely are actively, it's an area of active research. So here's an example of work that we've been doing in the area of fairness, which is important because many of the machine learning systems you train are on data sets that kind of reflect the world as it is and not necessarily the world as you'd like it to be. And how can you actually use biased and unfair data and actually affect change and make those predictions more fair than the raw data would generally indicate? Okay, so in conclusion, I hope I've convinced you that machine learning hardware is a thing and is going to be useful, and also that there are a bunch of breakthroughs happening through application of machine learning to a really wide variety of problems. I think that's what's really exciting here is people in all sorts of disciplines of science and engineering are starting to see that these sorts of approaches, learning from data, using these kinds of techniques, are really making forward progress in solving some difficult problems that have not been moving as fast as they were until we started looking at them with this lens. So with that, thank you very much, and I will take questions.